Section 9.4, two variances or standard deviations. Key concept. In this section, we present the F-test for testing claims made about two population variances or standard deviations. The F-test, named for statistician Sir Ronald Fisher, uses the F distribution introduced in this section. The F-test requires that both populations have normal distributions. Instead of being robust, this test is very sensitive to departures from normal distributions, so the normality requirement is quite strict. F-test with two variances or standard deviations. The following key elements box includes elements of a hypothesis test of a claim about two population variances or two population standard deviations. The procedure is based on using the two sample variances, but the same procedure is used for claims made about the two population standard deviations. The actual F-test could be two-tailed, left-tailed, or right-tailed, but we can make computations much easier by stipulating that the larger of the two sample variances is denoted by the following: S subscript 1 squared, which is the sample standard deviation squared, which is the same thing as the sample variance. Now, it follows that the smaller sample variance is denoted as S subscript 2 squared. This stipulation of denoting the larger sample variance by S subscript 1 squared allows us to avoid the somewhat messy problem of finding a critical value of F for the left tail. Hypothesis test with two variances or standard deviations. Objective. Conduct a hypothesis test of a claim about two population variances or standard deviations. Any claim made about two population standard deviations can be restated with an equivalent claim about two population variances. So the same procedure is used for two population standard deviations or two population variances. Notation. For population 1 and for population 2. So S subscript 1 squared is the larger of the two sample variances. S subscript 2 squared is the smaller of the two sample variances. N subscript 1 is the size of the sample with the larger variance. N subscript 2 is the size of the sample with the smaller variance. Population variance subscript 1 is the variance of the population from which the sample with the larger variance was drawn. Population variance subscript 2 is the variance of the population from which the sample with the smaller variance was drawn. Requirements. Number 1, the two populations are independent. Number 2, the two samples are simple random samples. Number 3, each of the two populations must be normally distributed, regardless of their sample sizes. This F-test is not robust against any departures from normality, so it performs poorly if one or both of the populations have a distribution that is not normal. The requirement of normal distributions is quite strict for this F-test. So, in number 1, you're going to state the claim and then the opposite of the claim. Number 2, you identify the null and the alternative hypothesis. The null hypothesis is the statement is assumed true until evidence indicates otherwise. The alternative hypothesis is the claim to be tested. There are 3 ways to structure a hypothesis test: two-tailed, left-tailed, and right-tailed. We would say that population variance 1 is equal to population variance 2 for all of the two-tailed, left-tailed, right-tailed for the null hypothesis. For the alternative hypothesis of the two-tailed, we would have population variance 1 is not equal to population variance 2. For the left-tailed, the alternative hypothesis is the population variance 1 is less than population variance 2. And for the right-tailed alternative hypothesis, population variance 1 is greater than population variance 2. Now, the alternative hypothesis is the one not containing equality, so the alternative uses the symbols less than or greater than or not equal to. Whereas the null hypothesis is the symbolic expression that the parameter equals the fixed value being considered. Number 3, you're going to use the alternative hypothesis to determine whether it is a left, right, or two-tailed distribution. Number 4, you're going to select the significance level alpha, and based on the seriousness of the type 1 error, you make alpha small if the consequences of rejecting a true null hypothesis are severe, and the values of 0.05 and 0.01 are very common. Number 5, the test statistic for hypothesis tests with two variances, with the null hypothesis being the variance of population 1 is equal to the population variance 2. So F is going to equal the sample variance 1 divided by the sample variance 2, where sample variance 1 is the larger of the two sample variances. Degrees of freedom. Now, the degrees of freedom is n1 minus 1. So the numerator degrees of freedom is n1 minus 1, and the denominator degrees of freedom is n2 minus 1. Okay, so number 7, we're going to find the corresponding p-value or critical value and then draw the curve and label. Okay, so for the p-value method, p-values are automatically provided by technology, and if technology is not available, then use the computed value of the F test statistic with table A5 to find the range for the p-value. For the critical value method, critical values are provided by technology or using the F distribution table A5. For significance level alpha, which is equal to 0.05, the two-tail test, the significance level of a 0.05 is divided between the two tails, so the area in the right tail is 0.025. A one-tail test, the significance level of alpha equals 0.05 is in the right tail. So let's open up the appendix. So here is table A5. So in the back of the book, if you're not using StatCrunch, then here, for when alpha is 0.025 in the right tail, so then we're going to use the values here for the degrees of freedom. This is the, if you look down here on the left side, this column here represents the denominator degrees of freedom. And then on the top, you have the degrees of freedom, the numerator degrees of freedom. If we move to the right, you can see here that it increases from 10 to 120. Again, we're using 0.025. Now, if we go one more to the right, now we're dealing with the fact that alpha is equal to 0.05. And again, the row on the top is the numerator of degrees of freedom. And then on the left here, this is the denominator degrees of freedom. So again, we would be using those values to find out what that critical value is going to be. Okay, then we're going to make a decision. So for the p-value, you reject the null hypothesis if the p-value is less than or equal to the significance level alpha, and you fail to reject the null hypothesis if the p-value is greater than the significance level alpha. For the critical value method, you reject the null hypothesis if the test statistic is in the critical region, and you fail to reject the null hypothesis if the test statistic is not in the critical region. Then you're going to state the conclusion. So if the original claim does not include equality and you reject the null hypothesis, you would state that there is sufficient evidence to support the claim that, followed by the original claim. If the original claim does not include equality and you fail to reject the null hypothesis, then you would state that there is not sufficient evidence to support the claim that, followed by the original claim. If the original claim includes equality and you reject the null hypothesis, then you would state that there is sufficient evidence to warrant rejection the claim that, followed by the original claim. And if the original claim includes equality and you fail to reject the null hypothesis, then you would state that there is not sufficient evidence to warrant rejection the claim that, followed by the original claim. Okay, now the F distribution. Now for two normally distributed populations with equal variances, the sampling distribution of the test statistic F is equal to the sample variance 1 divided by sample variance 2 is the F distribution, provided we have not yet stipulated that the larger sample variance is. Now, if you repeat the process of selecting samples from two normally distributed populations with equal variances, the distribution of the ratio is the F distribution. Now, there is a different F distribution for each different pair of degrees of freedom for the numerator and denominator. Okay, so if you take a look here on the figure to the right, okay, the F distribution is not symmetric. The values of the F distribution cannot be negative because you have 0 and everything to the right. And the exact shape of the F distribution depends on the two different degrees of freedom. Interpreting the value of the F test statistic, F distribution. If the two populations have equal variances, then the following ratio will tend to be close to the value of 1. Because we are stipulating that the sample variance of 1 is the larger variance, then that ratio will be a large number whenever the sample variance 1 and sample variance 2 are far apart in value. Consequently, a value of F near 1 will be evidence in favor of the population variance 1 equal to population variance 2, but a large value of F will be evidence against population variance 1 equal to population variance 2.